よろしくお願いします。My name's John Hawthorn. I'm a Ruby committer, a member of the Rails core team, and a staff software engineer at GitHub. You can find me online, various social media as J Hawthorn or some variation of that, so please say hi in person or online. I joined GitHub in 2018 as a member of the Ruby architecture team. My team is responsible for upgrading Ruby and Rails and developing those frameworks so they better meet GitHub needs, as well as integrating them into GitHub's code bases. This talk is about how we've scaled Ruby at GitHub, some stories about techniques we use. Most of these are things we've been using for many years, so we can trust that they work. And for a sense of the scale that GitHub's now at, GitHub recently announced that it is the home for 150 million developers. So that can give you a sense of how far something that started as a little Ruby application can go. So when we talk about scaling, I think there's actually two separate concepts we're talking about. There's scaling users and scaling teams. When scaling users, that's having more customers, more traffic, more web servers, whereas scaling teams is more developers, which usually means more lines of code, either total or the number of lines of code that are changing, as well as more features. There are some, for most organizations, these are going to grow together. Having more customers are going to want more features. Having more customers lets you have the resources for more developers. So there's some exceptions to this, but for most companies, both of these will grow together. In GitHub's beginnings, it really just was a single, simple Ruby and Rails web application. And it's not just that GitHub used Ruby and Rails to build the product. The founders would go to conferences like this one and share what they were building with the Ruby community. A huge number of all the early users of GitHub were Rubyists. And it's not just GitHub that owes its success to the Ruby community, but Git as well. Git's creator, Linus Torvalds, says that it was Rubyists using Git that really made it take off. When GitHub was started in 2007, and when it first launched the following year, that was running on Ruby 1.8. This was around the start of that awkward 1.8-1.9 transition period, and the string encoding changes were actually that came with that were actually very challenging for GitHub. Git data is all binary. The files are binary. The branches and file names aren't necessarily UTF-8. So it was pretty difficult for that upgrade to happen. And what actually ended up happening is GitHub forked Ruby and had a version of Ruby 2.0 which had some looser string concatenation rules that let 1.8 code still be compatible. This was well before my time at GitHub, but they really wanted the performance optimizations and particularly the GC improvements that came with later versions, and so had to do a lot of extra work to get those. Eventually, it was able to get back to mainline Ruby releases and has been up to date since then. There's a similar story for GitHub's Rails upgrades. It started on Rails 1.2, was able to migrate all the way to 2.3 before a similar problem happened, and some compatibility problems with 3.0 mixed with some fears about performance stalled further upgrades. And GitHub ended up building a non-trivial fork of Rails, which had some of its own features and behavior changes that made it different than what you'd see in a standard application. And this wasn't great because it meant that people joining the project needed to learn a whole new set of different rules, and things weren't aligned with the community. Fortunately, due to a lot of effort, both within the GitHub code base as well as upstream in Rails, eventually, shortly after I joined, GitHub was able to upgrade to Rails 4.2 and then 5.2, which at the time was the latest version. Today, GitHub runs Rails 8.1 alpha in production. Yes, that's a version that's not even out yet, so we're very up to date. We try to upgrade Rails every single week from the main branch. We have a scheduled GitHub action that pulls down the Rails source code, builds the gem, upgrades it, and automatically opens a pull request. We'll then go review that pull request and try to merge it. For Ruby, we're currently running Ruby 3.4.1, the latest version as well. For the last 3 years, we've been able to upgrade our production hosts to the latest Ruby in January, within 1 month of the new version coming out. We're also running YJIT. We've been running YJIT since Ruby 3.3. When we switched that on, it gave us a 15 to 20% performance improvement. It depends on the page, depends on what it's running, but it's been very helpful. And things like this are one of the big motivations for us to keep up to date and to keep upgrading. Similar to Rails, we try to upgrade Ruby most weeks. We don't run the unreleased versions of Ruby in production, but we do run them on a CI job. And that lets us make sure that we're staying compatible. It allows us to use GitHub's test suite to find bugs in Ruby upstream, get early notice of any deprecations, and really do this work incrementally so that we can upgrade as soon as the new Ruby version is available. So for both the language and framework, upgrading weekly lets us make smaller changes, stay closer to upstream, as well as it encourages us to contribute upstream to Ruby and to Rails. Before, when GitHub fell behind, it was really hard for us to participate in the community and make changes to Rails because we wouldn't know how long it would take for us to see them. When we're upgrading regularly, we at least know how long. If we make a change to Rails, the lead time for seeing that in production for our website is only 1 week. For Ruby, it's a little more, it's up to a year, but we can make backports to allow that. And so that lets us see the language and framework as not a totally separate thing, but something we're participating in. It's an extension or a part of our application. So when I'm talking about Ruby at GitHub, I'm largely talking about our largest application, which we call the monolith. This is we have various other services in various other applications we run in a variety of languages, including others in Ruby, but this is our largest, most active application, and it's the original application that GitHub was founded on. And my first impression of it when I joined GitHub was that it was a surprisingly normal application. If you were familiar with what Rails applications look like, it seemed to have the things you'd expect it to. It had models, controllers, jobs, and again, this isn't an accident. It's what we wanted to see. As much as possible, we wanted to follow community standards so that we can benefit from all the work in gems. People can read the public documentation, and if they have past Rails experience when joining GitHub, they can use that. One thing that's not normal about the monolith is its size. It's approaching 4 million lines of code. More than half of that is tests. We have 1,000 developers working on it. Some full-time, others will dip in and out. And it ships 2,500 pull requests a month. So it's big. This creates some problems. I can't read 4 million lines of code. If I could, I wouldn't remember what they did. And I definitely can't review 2,500 pull requests. So we need to find some way to split up these responsibilities. One tool we use very heavily is called code owners. This is a small standard GitHub has been pushing. So this is a file at the top level of the repository that has glob patterns similar to a git ignore file. And then it associates those files with a given team. And the nice thing about developing GitHub on GitHub is we can put features into the product that help us, and then hopefully they help our users as well. So when you open a pull request and you have this code owners file, it will add the relevant teams, the matching teams, as a reviewer. So that automatically gets the pull request in front of the right people who then have to approve it. We also use code owners for error attribution. So when we have an error in production, before we send it off to our error monitoring, error tracking service, we do some processing on the backtrace. First, we filter out irrelevant lines based on a set of hard-coded rules, and then we'll perform the code owners matching at runtime to figure out which team we think owns that. And there are many lines in a backtrace, and I think it's kind of impossible to say which line is the most relevant, but we found to be useful is to get the deepest line of the backtrace and find the team for that, and the topmost line from the backtrace and find the team for that. So we think of that as one of these being the service, so probably the page someone was visiting that encounters the error, and the other one being a likely cause. So maybe that's the code that was doing something it shouldn't that caused the error. So this helps us know who to page or which team should be responsible for fixing a problem. So code owners is really great. It's something we have a lot of success with, but not everything can be divided by file. But there's some workarounds we found that are very helpful in working around this. So something, for example, something my team wanted to do recently is remove OpenStruct from our code base. OpenStruct has some performance problems. It doesn't play the best with YJIT, and it's being removed from default gems in Ruby 3.5. You can always include the gem, but we felt it was time to get rid of that so there wasn't a performance pitfall people could fall into. And so what we'd like to do is make a new file that's a linter to verify that there's no that OpenStruct doesn't appear anywhere in the code base. We could do this more correctly with Rubocop or parse out constants with Prism, but a text match is good enough for this example. The problem is when you're working in a large code base, it's really hard to get to zero, to actually fix all of the OpenStruct cases and get all of them. Because as we're doing this, as our team is doing this work, other teams are going to be adding and changing code. And they might even be adding more uses of OpenStruct faster than we can remove them. So the first thing we need to do, rather than changing the assertion to zero, is change it to whatever the current state is, just to make sure the problem doesn't get any worse. Then we can add this linter file, our team as the owner, as the code owner for this new linter. So we'll have to approve any changes which are trying to add a new OpenStruct. Then to make this a little bit better, because when someone adds, we don't have the opportunity at a team of our size to educate everyone on why OpenStruct is bad. I don't want to make a Zoom meeting with 1,000 people and take an hour of their time to explain this. So we really need to use our tests and our linters as a communication tool. So here we we'll check if someone has added an OpenStruct and then use the code to educate them on why that's a problem and what they can do to move forward. And we found it's very, very important to give very concrete steps. And I like to call this the ratchet technique because we're trying to tighten this constraint. We're trying to keep the OpenStruct count going lower. So after we do that, maybe we do all the work, maybe we found some automated way to do it, and we have some large commit to remove all the OpenStructs. That's going to have some of the same problems. We're probably not going to be able to ship this. It's too big, too hard to review, and we don't want all the teams to review thousands of lines. And if any of them have objections, then we'd have to start the whole process over. So a tool we sometimes use for this is we have a script to take a large commit and break up all the files in it by code owner. and then automatically open a pull request for each one. This way, teams only have to review the code that's relevant to them. And we can ship all of these separately, making small incremental changes, which is what we're always aiming to do. So that might help explain why we're deploying so many pull requests, 2,500 a month. And we do currently about 20 deploys a day. And at times in the GitHub's past, it's been higher, but that's the pace we're able to do today. And if you divide 2,500 by 30, you can't deploy that many pull requests. We don't have enough deploys in a day for each one to be a single pull request. And this is a problem I think most large organizations end up with, is being bottlenecked on being able to deploy. So GitHub's always favored branch deploys, where the main branch is always code that's already been in production, rather than merging into main and then deploying main to production. We think this is just a bit safer, and it means that all the new branches that are based off of main always have code that we trust. And so in GitHub's early days, this wasn't really a problem. We'd just be able to deploy a branch, and if someone else was busy, it shouldn't take long before they were done deploying. Building on that, eventually there was a queuing system where we'd have to take turns. You'd deploy your pull request, and then someone else would come along, or someone would be deploying, and you just have to wait your turn. But at some point, this queue became too long to be viable. I'd queue up first thing in the morning, and I wouldn't be allowed to deploy by the end of the day. So more recently, we've built another feature into the product, the merge queue. This is publicly available, which allows grouping up pull requests together. So you declare that in the web UI that you want to merge a pull request, and it will try to group a bunch together, make sure they're all passing CI, including after they're merged, and then makes a queue of those. Those have been very helpful, but like everything, there can be some issues. If one of these PRs has a bug, we need to revert the whole group. And not only does that delay this group, and everyone will have to queue back up, but it delays the following group. So it's it really slows down everyone's development. And this is really a pattern we'll see, that as an application grows, the cost of having a bug in production grows as well. Not only do you have more users, so more users to see the bug that you've introduced, but it slows down more of your developers. So a feature many probably have heard of or used that helps us a lot with this is feature flags. And we use feature flags an incredible amount. Feature flags let us separate the deployment process from the new code being run in production. So in their simplest form, you'll just check, you can just ask whether a feature by some given name is enabled. And there are various ways you can then have a backend for this. We have a database with a caching layer in front of it. And that allows, and then you can configure this to be fully enabled, fully off. But what is very helpful is you can turn it on slightly. You can have a random percentage of the time for this to return true or false. So that lets you ship incredibly slowly. You can have something you take a whole week to turn on a feature. A more advanced way to do this is you can pass in an actor. This is with a open source library called Flipper, which our feature flags were based on. You can pass an actor as well, so maybe you want to enable it for just a certain user or just a certain organization. Or you can also do the randomness on the user or organization. So if it's something visible, a visible change, you don't want it changing for a user as they're refreshing. So doing a random thing that's based on their ID or username can be helpful. And this is a good technique to understand how it works, because some changes aren't viable to make in a traditional feature flag, but we still want to have that slow rollout process. So when we enabled YJIT last year, a simple thing we could have done is had an environment variable to turn YJIT on. But that's a very big change to make all at once. And there's some aspects of that, using more memory, having to spend CPU on JIT compiling, that it's really hard to predict how that's going to work in production until it's actually shipped. So we wanted a slower way to roll that out. And you can use the exact same technique just by doing it explicitly. You can use an environment variable to, rather than say enabled or not enabled, to tell it the percentage you'd like to enable. And if you want it to be more consistent, you can even make that randomness based on the host name. And this is a technique we've used a lot over the years. Going a step further than feature flags, a lot of the time what we're doing when we're trying to improve performance is to replace one implementation with a new implementation that's faster. So Scientist is a tool from GitHub that allows comparing two implementations. So here's essentially the pseudocode. So if we have some piece of code that we're running and works, but maybe want to change it in some way, what we'll do is we'll add a call to new code that should be doing the exact same thing as it, and then we'll just have a test that the result of those two is equal. And if not, we'll report an error. So Scientist is a nice library in DSL to wrap that concept. You give it a use block, which it runs every time, and that's the result that's returned. And then you give it a try block, which isn't used ever. It's just compared to the use block. So if you ship this and everything, and you don't see any errors, you know it's safe to switch over to the new code. This also records the mismatches. In an ideal world, maybe tests would catch all of them, but it's very helpful in production for it to figure out if there's any cases that tests weren't covering. As well, this nicely sets up a feature flag, so we can gradually turn on the try code just to make sure there's no other problems with it. And then it reports metrics of both, so we can make sure that the new code is actually faster as we expected it to be. So Scientist is a great way to make code faster, but one thing we then need is to figure out what code, what parts of our code are slow. And we give to staff a utility that I really recommend anyone trying to make their website faster or grow their code is some sort of performance toolbar. So we have a staff bar that's not open source, but Rack Mini Profiler is an open source tool I really recommend. And it's really best to run in production and make as easy as possible for developers to get the information from it. For us, it's nice to have our own because we can add things that are especially relevant for GitHub. We have a count of our feature flags. This page apparently had 200 to give you an idea of how much we like feature flags. We have profilers that are easy to get to, and then usually for scaling, the thing that ends up being the most important is database queries. So for database queries, GitHub we've actually written our own MySQL compatible database client called Trilogy. This is an open source library. You can go check it out. It's fast. It's a re-implementation of the wire protocol, so it doesn't depend on any libraries, which is, if you've ever tried to, I feel like every time I try to bundle install a database adapter, I get an error because I haven't installed the right library. So it avoids that, and it's embedding friendly. So it's really designed to be well integrated with the Ruby interpreter. And it's able to use Ruby APIs for waiting on I/O and such, so it ends up being fiber compatible and having other nice properties. So please check out Trilogy. So moving on to database scaling. When you start out, you'll generally have one application server talking to one DB server. And it's relatively easy to go from there and to add another app server and another app server. Usually they're stateless, so there's really no limit until eventually you have way too many app servers and your database completely falls over. And so this is, I think, where the scaling machines part usually ends up coming in. And there's a lot of different techniques, but the one, I think the most foundational to GitHub success has been to have database replication. So with replication, you have a primary server, and then all the data to that is written to read-only replicas. And so you can only write to the primary, but then you're able to read from the replicas as much as you want. And so that's a very easy way to scale out your database infrastructure. One concern about this, though, one thing you have to look out for is that there's a replication delay. Usually it's pretty good. I think we would consider anything more than a second to be a lot of time, but that's still a delay, so it's something you need to look out for. This is something that's actually now built into Rails. It was originated in GitHub's codebase, but was lifted up into Rails. So you can write a configuration in your models and then update your database YAML, and then use this connected to block, which sets a thread local and allows querying the replica. And yes, it's available since Rails 6. This originally came from GitHub, but this is one of the benefits from us keeping up to date, is we've been able to take the things we're doing internally and share them upstream. And so in some cases, you might be able to just find a particularly expensive query or a query that you don't mind if it's out of date. But in other cases, we really want to automatically send as much data to those replicas as possible. One simple scheme might be you'll take all logged in users get up-to-date data, and any anonymous users you send to replicas, because they're probably not writing, so it doesn't matter if their data is slightly stale. And how much benefit this gets you depends on your distribution, but let's say it's 50-50 logged in anonymous. That would get you 2x scale, which is, maybe not too bad, but isn't necessarily going to get you to the scale you need. So to do better, we need a way to find, to get our logged in users data from replicas. And one of the simplest schemes is simply say, have they had a write recently? When was their last post request? So we can record that, and then if they haven't had a write recently, the data may be stale, but it's not their data, so they probably won't notice or mind. It's eventually consistent in a way that's not noticeable or painful. And so this too is something that has been built into Rails, and you can configure it relatively simply. At GitHub, we've since outgrown this as well, and have a tool that allows not only having the 1 second delay, but making it dynamic based on what we're seeing in production. So Freno is a Go application that we've open sourced, and you can use, it will continually monitor a MySQL database to find the replication delay, and then we have a Ruby client for it that can check and then figure out how to forward things that way. And so doing this, we actually can get 98% of the time, even a logged in user can be sent to a replica. And so inversing that, that gives you 50 times scale on your databases. So there's, I think, any form of replication is extremely effective, and I think it's the first thing an application should look at if you're starting to push the limits of what you can do with a single database. There's much more, many more techniques like this, but this is the first thing I wanted to share as the first steps to take. But there's more built into Rails and more techniques and more things all the time. One thing we've been working on upstreaming recently is database retries. When you have these replicas, that implies you have more points of failure. They're hopefully not single points of failure, but because there's more machines, we're going to have to restart them more often, or even reap the connections so the load balancer can move them around, so we can make sure the load balancing works properly. And so we don't really want users to be impacted by that. We don't want them to see that as a problem. And so a thing we've had for a long time is automatic database retries. So when a query is run and it fails, we'll automatically retry it against another replica, or it will reopen the connection and try again. This is mostly default in Rails. For many queries, this will all happen automatically. And it is, again, something we've tried to lift out of our code base and share with the wider community. I will admit we have one hack that really helps us out, which is to assume that all queries are retryable. We know in our application this is true, but it's Rails itself tries to be a bit more conservative and only retry queries that it knows to be idempotent. But please don't copy this. We should make it work better by default. You can also, there's some configuration available for this. Setting the connection retries can be configured, as well as a deadline can be configured to only retry if it's not taking too long. So this is great, but again, fixing these problems causes new problems. Retries can hide unhealthy systems. If you need to have good metrics to know that one unhealthy replica isn't sitting there with no one noticing because all of the errors are hidden from users. It's great they're hidden from users, but not good to have unhealthy systems. The other thing is that retries, when a problem is encountered, you can end up creating a self-denial of service of your systems. If you keep retrying and retrying, your database might not be able to recover from whatever temporary problem it had, because it's continually receiving more and more traffic. The technique we use to try to mitigate this is, it's a little bit counterintuitive. So circuit breakers are a technique that has really been championed and pushed by Netflix engineers, which is to have errors happen. It's counterintuitive. It's to have errors happen more often, but for those errors to be faster and to not impact the systems they're talking to. So the idea is you create a circuit breaker by a key, not unlike a feature flag, and then you check whether it's allowed to be run. And then if it sees a certain number of failures, it will tell you to stop trying, to eventually give up. Much like a circuit breaker in a house that will just turn off all the power. So for databases, we're able to do this by making a trilogy class that just delegates to the other one, but introduces synthetic failures when we cross over the threshold for the circuit breaker to trip. This doesn't have a fallback, so I don't know, so I would caution against applying this without a lot of testing and care, because it might make your systems fail more rather than work better. But at a certain scale, this is a very helpful thing to keep all of the systems running healthy. So I hope this has presented a taste of running Ruby at scale, where you can take a Ruby application. I hope this gives you confidence in choosing Ruby and building with Ruby, that there are options as you grow into that scale. I've been trying to think about taking the language framework and all the libraries we use, not as independent things, but a part of our application, something we want to develop and make scale so that other applications can grow into using these tools as well. Let's scale Ruby together. Thank you. Arigatou gozaimasu.